Welcome dreamers and participants. This is Ravindra Thube, faculty at BYJU'S Exam Prep, and I welcome you all to one more scintillating session of a daily dose. Here I am going to discuss Shastras and Asras which are going to use to solve beautiful numericals on a metal cutting. We know that metal cutting is the most important topic of a GATE examination. Every year questions are there, so many formulas are there, and while solving numericals, students are committing a lot of mistakes. So let's understand what Shastras and Asras will give you a lot of ease and comfort while solving numericals. So let's say that the first, whenever it is given in the problem, merchant's first solution. The merchant first solution is nothing but a equation developed to consume minimum energy, minimum forces and minimum power. So whenever there are multiple words are coming in GATE examination for merchant's minimum energy, minimum power consumption, minimum forces, or by merchant solution calculate shear plane angle phi or whatever it may be, then we have to use merchant's equation for minimum energy, and that merchant's equation for minimum energy is exactly 2 phi plus beta minus alpha 0 is exactly equal to 90 degree. This is called as merchant's first solution or called as merchant's first or merchant's equation for minimum energy. Merchant's equation for minimum energy. The moment it is written in a GATE examination that use this, that is minimum energy, minimum forces, minimum power consumption, it has to be used 2 phi plus beta minus alpha 0 is equal to 90 degree. Now there is merchant's second equation is also, or second solution is there. And what is merchant's second solution? Merchant's second solution stands for 2 phi plus beta minus alpha 0 is exactly equal to a cot inverse of k. Cot inverse of k. Phi is shear plane angle, beta is friction angle, alpha 0 is rec angle, and k is nothing but the slope of the graph, right? How the deformation takes place. Now here there is one machining constant is calculated called as Cm, and that machining constant Cm is exactly 2 phi plus beta minus alpha 0. Multiple times number of questions are coming. Calculate a machining constant. So machining constant is exactly equal to Cm, that is 2 phi plus beta minus alpha 0. And if this machining constant is exactly 90 degree, can I say that efficiency of machining is exactly equal to 100%? You must have understood and heard about this particular. So if I say merchant's second solution is 2 phi plus beta minus alpha 0 is equal to cot inverse of k. Now sir, there is one more thing is coming in a metal cutting operation. Whenever the force is applied, there is a shearing takes place, and because of the shear plastic deformation, the layer will start sliding away from that particular tool, and therefore the material removal takes place. And therefore question is asked minimum shear strain condition. Minimum shear strain. What is the shear strain? The shear strain is exactly equal to cot phi. Shear strain is exactly what? Cot phi plus tan of phi minus alpha 0. Cot phi plus tan of phi minus alpha 0, because we know that here whenever we are talking about any kind of metal cutting operation, I'll say that there are three velocities comes in the picture. This is called as cutting velocity Vc, that is velocity of the tool with respect to workpiece. Then along the shear plane there is a shearing takes place. So what is the velocity by which shearing takes place? The layer of the material or chip is sliding, that is called a shear velocity Vs. And once the chip is manufactured, can I say that it will start sliding over the rect surface? It is slide over the rect surface by velocity called a chip flow velocity Vf. Angle made by shear plane with cutting velocity vector is called a shear plane angle phi. And generating the minimum shear or generating the shear strain, calculate the shear strain is what equation? Cot of phi plus tan of phi minus alpha 0, which means that shear strain is basically a function of a shear plane angle phi comma rec angle alpha 0. But rec angle alpha 0 remain constant because it's a tool geometry. So shear strain is function of a shear plane angle phi. Now if I want to generate minimum shear strain, differentiate this equation with respect to phi, and because of the differentiation you will get one particular relation that is called as a minimum shear strain condition, and when it is given in the problem we have to use 2 phi minus alpha 0 is exactly equal to what? 90 degree. The moment you observe that it is written in the GATE examination problem minimum shear strain, so I have to use equation 2 phi plus beta minus alpha 0 is 9. What is that? 2 phi minus alpha 0 is equal to 90 degree to calculate shear plane angle phi or whatever it is asked. Minimum shear strain condition. Now sir, whenever generally in metal cutting operation, can I say that my cutting force used to be greater than the thrust force? And if my cutting force is greater than thrust force, which will observe that the friction angle beta will come less than or equal to 45 degree, and coefficient of friction mu will also come less than 1 value, and it is very accepted as far as metal cutting analysis is concerned. But there are some typical metal cutting operations are there, like a grinding process, where it has been observed that very typically the value of my thrust force becomes greater than the cutting force. Which value of force is becoming greater? Thrust force becomes greater than cutting force. And when the thrust force becomes greater than cutting force, if I use a conventional equation developed from the Merchant circle diagram to calculate the friction angle beta or calculate coefficient of friction mu, and what is that formula? That simple formula is tan of beta minus alpha 0. Tan of beta minus alpha 0 is exactly equal to Ft divided by Fc. Ft divided by what? Fc. Tan of beta minus alpha 0 is exactly equal to Ft divided by Fc. So if I use this formula, you will observe that the friction angle beta value will come greater than 45 degree, and simultaneously the coefficient of friction mu will exceed value of 1, which is not accepted generally. And therefore in this case, this particular equation tan of beta minus alpha 0 is equal to Ft by Fc fails, and therefore at that point Cronenberg's equation has to be used. And the Cronenberg's equation tells that the coefficient of friction mu is exactly equal to ln 1 by r, ln 1 by r divided by pi by 2 minus alpha 0, divided by pi by 2 minus alpha 0. Rectangle has to put in the value of radian, and r is nothing but called a chip thickness ratio. R is what? Chip thickness ratio. T naught by Tc, or number of formulas are there by which this chip thickness ratio can be calculated. So therefore we can say that, sir, by Cronenberg's equation we have to calculate the coefficient of friction mu. So you have to understand that whenever the question is being given, you have to find out that which force is greater. If the cutting force is greater than the thrust force, normal equation you can use it by default. But if the thrust force is greater, please remember that the Cronenberg's equation has to be used to calculate the coefficient of friction mu, and then the friction angle beta also can be calculated from that particular formula. Now let's say that, sir, generally it has been observed that sometimes whenever we solve the numerical, so what is the side cutting edge angle CS, or what is exactly equal to principal cutting edge angle, that is lambda. So this is lambda value, right? Fine, is not given in the problem. And without that clarity, what is the side cutting edge angle CS and what is the principal cutting edge angle lambda, I can't be able to solve numerical. And therefore can I say that, sir, it has to be observed that we have to assume sometimes, if nothing is mentioned clearly into the GATE examination problem, we have to assume that the side cutting edge angle CS, we have to assume that a side cutting edge angle CS will be exactly equal to, side cutting edge angle CS is exactly 0 and principal cutting edge lambda is exactly equal to 90 degree, which means that this lambda becomes what? 90. Whatever figure is drawn here, can I say lambda is equal to 90 degree. So in addition to inclination angle to be 0 for orthogonal cutting operation. So in addition to I, we have to assume that CS equal to 0 and lambda is equal to 90 degree. That means it has to be assumed the machining is a pure orthogonal cutting operation, and then rest of the analysis has to be done. So therefore you have to remember that if nothing is mentioned clearly in the problem, then assume side cutting edge angle to be 0, principal cutting edge angle lambda to be exactly 90 degree. Here CS is exactly 0 degree. Please remember this, very, very important as far as solving number of numericals are concerned. Now while solving numericals, number of times you get confused between depth of cut, width of the cut, uncut chip thickness and so many parameters. So there are three particular cases are developed, and based on that entire numericals of metal cutting operations can be solved with ease, which is most important. So let's say that we have assumed that now if the uncut chip thickness T0 and width of cut W0, that we have to understand, because without that uncut chip thickness T0 and width of the chip W0, the numericals can't be able to solve. Numericals cannot be able to solve. So how to decide this uncut chip thickness T0 and width of the chip? Because width of the chip anyway remain constant before, during and after deformation. That's why there is a plane strain metal cutting operation comes in the picture. So therefore we assume that, sir, let's not assume, suppose the feed is given to you in the problem, that is F, and depth of cut D is given. Depth of cut D is given, the feed is given. Depth of cut D is given and feed is given. So in that case, you have to assume that if case number 1, what is the case number 1? Depth of cut is given and feed is given. So if it is a pure orthogonal cutting operation, that is lambda is equal to 90 degree if it is there, or CS is exactly 0 degree, that is what pure orthogonal cutting operation. In such a case, so this is exactly equal to my depth of cut D, that is perpendicular distance between atmospheric surface and machine surface. Can I say that will become exactly equal to width of the chip WC? So therefore here can I say that my width of the chip becomes exactly equal to depth of cut, or depth of cut becomes width of the chip. Width of the chip is exactly depth of cut, and my feed will decide uncut chip thickness. So uncut chip thickness T0 you can exactly equal to feed. Very, very important while solving the numericals in GATE examination. So what, when depth of cut and if feed is given, feed becomes uncut chip thickness, and depth of cut will become exactly equal to width of the chip, width of the chip, width of the chip. Right, fine. Next question or next. Sir, previously we have discussed that, okay, fine, it is given, but I have assumed that lambda is equal to 90 degree of C is equal to 0. If it is given, if not, if lambda is not 90 degree, if lambda is not at all 90 degree, or CS is not exactly equal to, CS is not exactly to 0 degree, then it has certain value. So in this problem, we can easily understand that this is exactly equal to a lambda, that is approach angle or principal cutting edge angle, and definitely it is not a 90 degree, and this angle is exactly equal to what? CS, that is called a side cutting edge angle, side cutting edge angle is also not 0. In that case, can I say this is exactly what width of the chip is coming? This is exactly equal to depth of cut, and therefore it has to be observed that, and already formula is developed. What is that? My feed becomes uncut chip thickness T naught into what? Sin lambda, sin lambda. Most of the times it has been observed that students don't follow this. ESE system of tool geometry or ORS system of tool geometry is given. Please find that what is the value of principal cutting edge angle lambda. If it is not, lambda is not 90 degree, then we cannot take the feed is exactly equal to directly uncut chip thickness T naught. It has to be calculated F is equal to T naught into sin lambda. Derivation is already there. You can check the derivation. And what will become width of chip? So can I say that width of the chip will become exactly equal to depth of cut divided by sin lambda. Depth of cut divided by sin lambda. Depth of cut divided by sin lambda. Don't take width of the chip is directly exactly equal to depth of cut. When lambda is not 90 degree, CS is not 0 degree. My dear friends, right, fine. Now the next case, in GATE examination, suppose depth of cut is given, width of cut is given relatively. So this is the one hypothetical figure is drawn as far as understanding point of view is concerned, right, fine. Either you can say that, sir, it can be considered as shaping or planing operation also to get a feel how exactly these dimensions are considered. So here it is nothing but called as a width of this particular cut, right? Width of the cut B, it is given width of the cut, and this is nothing but a depth of cut. And now this chip is coming out. So can I say that, sir, whenever this chip is coming out, the chip will be having certain dimension. So you tell me that, can I say that as far as chip is concerned, as far as this chip is concerned, can I say that this dimension will be exactly equal to width of the chip? Can I say this dimension will be exactly equal to width of the chip? And can I say this dimension will be exactly equal to a thickness of the chip, thickness of chip. So can I say thickness of the chip? You can easily understand this thickness of the chip will be controlled by depth of cut, thickness of chip will be controlled by depth of cut, and width of the cut will control by width of the chip. Width of the chip is controlled by width of the cut, and therefore can I say directly I'll write down here. Can I say that, sir, width of the cut will become exactly equal to width of the chip is exactly width of the cut, and can I say that this chip thickness is exactly equal to depth of cut. Chip thickness is exactly equal to depth of cut without any doubt. Without any doubt. Is it okay? Right, fine. Next question. Next particular. Suppose if the feed is given and width of cut is given. So whatever previous two cases we have discussed, it is the combination of these two cases. What is given? Feed is given. So can I say if the feed is given, can I say that, sir, T naught uncut chip thickness will become exactly equal to feed, and width of the cut is given. So can I say that, sir, width of the chip will become exactly equal to width of the cut B, but this is only happen for what? When lambda is equal to 90 degree, lambda is equal to 90 degree, or CS is exactly equal to 0 degree. For only this case it has happened. Or if lambda is not 90 degree, if lambda is not 90 degree, or CS is not exactly equal to 0 degree. So then I say that, sir, uncut chip thickness T that will become exactly equal to what? F into sin lambda. F into what? Sin lambda. Do you understand that? F into sin lambda. Very, very important thing. Very, very important thing. T naught is exactly equal to F into sin lambda. Right, fine. And we have to understand that. Right, fine. Now, sir, there are three velocities comes in the picture. One is called as cutting velocity VC. Second is called as shear plane velocity VS. And third is called as VM. Right, fine. Now there is a relation between them, and that can be developed with the help of a velocity triangle. So you don't require to go and mug up this formula. Just understand this triangle and try to make a habit of drawing this particular triangle. So if I draw here horizontal line, that can be represented by reference plane. So therefore I'll say that, sir, there will be a one angle is coming here. So can I say this angle will be exactly rect angle alpha 0. Right, fine. Now I'll draw one particular line here. So this will be exactly equal to representing a chip flow velocity, right? This line will represent a shear velocity, and whatever cutting velocity is there, to complete this triangle, I'll draw cutting velocity at this particular location. So I'm getting one particular triangle. This is exactly equal to cutting velocity VC. This is shear plane velocity VS. This is chip flow velocity VM. Now we have to just set these particular angles. Angle made by shear plane with cutting velocity vector is shear plane angle phi. Is what? Shear plane angle phi. It is what? Shear plane angle phi. So therefore, can I say that, sir, this angle will become exactly equal to, what is this angle? What is this angle? This will become 90 minus phi, 90 minus phi, 90 minus phi. This is alpha 0. Now, if this is 90 minus phi, this is alpha 0, can I say that it will become exactly equal to 90 minus phi minus alpha 0. Do you understand that? This angle will become exactly equal to 90 minus phi minus alpha 0. 90 minus phi minus alpha 0. So, I have to put this in the bracket, 90 minus phi minus alpha 0. Is it okay? This is phi, this is 90 minus phi. So 90 minus phi plus this alpha 0, this is 90 minus phi minus alpha 0. Yes, is it accepted, everybody? Yes. This is what exactly, I'll say that this will be exactly equal to alpha 0. If this is alpha 0, can I say that this is my right angle triangle? This is my right angle triangle. So what will be this angle? This is 90 minus alpha 0. Yes, correct. So therefore I can write down here, this will be exactly equal to, 90 minus alpha 0. 90 minus alpha 0. Right, 90 minus alpha 0. Right. Now what will be this angle? Sir, this is equal and opposite of shear plane angle phi. So this will be exactly equal to phi. And therefore, now we can apply sine principle, VC divided by sine of 90 minus phi minus alpha 0, VF divided by sine phi, and VS divided by VS divided by sine of 90 minus alpha 0. So don't require to mug up these formulas. Just try to find out how exactly sine triangle can be drawn at immediate basis. Right, fine. Now, determination of forces can be done with the help of a merchant circle diagram. And just understand how exactly merchant circle diagram is getting developed. So, along the shear plane, along this rake surface, there is a friction force acting. So, therefore, I can write down here, this is exactly equal to friction force F. Normal to friction force, can I say there will be a normal force acting. A resultant of that is exactly equal to R. Exactly equal to R. So, along the shear plane, shear force is acting. So, I'll say that this will be exactly shear force S. And normal to that, can I say that there will be normal to shear force acting NS. This is exactly equal to my cutting force FC, and this is exactly equal to my thrust force FT. So there are three right angle triangles. There are what? Three right angle triangles is included in that particular circle, and the circle diameter is exactly equal to resultant. Now angle made by a rake surface with the reference plane is orthogonal rake angle alpha 0. So this angle will be also exactly equal to alpha 0. This angle is exactly equal to what? Beta, because we know that tan of beta is equal to F divided by N. So this is not NS, it can be normal to friction force F. Now if this is beta, can I say this angle will be exactly equal to what? This is entire triangle. This is entire triangle. So this is beta. This is what exactly become what? 90 minus beta, because this is 90. So we can write down this will be exactly equal to 90 minus beta. Now we can easily understand that, sir. This is horizontal, this is vertical. Right, this is 90 degrees. So 90 minus this angle will be what? 90 minus beta plus alpha 0. So therefore it will come what? Beta minus alpha 0. It will come what? Beta minus alpha 0. Angle made by shear plane with a cutting velocity vector, that is exactly equal to shear plane angle phi. And from this merchant circle diagram, you can set the relation between a cutting force and thrust force Ft. These are measurable forces. These can be set a relation between friction force or normal to friction force, or a shear force or normal to shear force. The relation between them can be set with the help of this trigonometry, and any unknown values can be calculated. Don't mug up this formula. Just remember how this merchant circle diagram can be drawn. Is it okay? Yes. Fine. Now the shear stress. Now we know that, sir, this is exactly equal to shear area. Right? Fine. This is exactly equal to width of the chip. This is uncut chip thickness T0. Angle made by shear plane with cutting velocity vector is shear plane angle phi, and this is exactly equal to length of the shear plane. Length of the shear plane. So how much will be length of the shear plane? Again, I'll say that, sir, length of the shear plane is very simple. From this triangle, sine phi is exactly equal to T0 divided by Ls. T0 sine phi is equal to a T0 divided by Ls. Right? I can write on here sine of phi is exactly equal to opposite T0 divided by Ls. So can I say length of a shear plane is exactly equal to length of shear plane is T0 divided by sine of phi. Sine of phi. This is one equation is coming. This one equation is coming. Right, fine. Now we are interested to calculate area of the shear plane. So can I say that area of the shear plane is exactly equal to the width of the chip multiplied by length of the shear plane. That is exactly equal to T0 into W0 divided by sine phi. T0 into W0 divided by a sine of phi. Now along the shear plane there is a shear force acting, right? Along this shear plane there is a shear force acting Fs, and normal to that there is a normal to shear force also acting. So because of the shear force there is a shear stress is developed. Because of the normal force there is a normal stress will be also developed. So what is the magnitude of that? So it's very simple, that shear stress along the shear plane is exactly to shear force divided by a shear area, right? So tau S is exactly equal to shear force divided by shear area T0 into W naught divided by sin phi. So sin phi will come to the numerator. This will be equation is coming. Same thing, because of the normal force, there is a normal stress is developed. So therefore normal stress is exactly equal to normal force divided by a shear area. Again the shear area is remaining same. So normal force or generate normal stress, and the shear force develop a shear stress along the same shear area. Along what? Same shear area. You can be able to calculate that. Right, fine. Now sir, between this any problem you solve in metal cutting, but chip thickness ratio is the basic thing that we have to calculate. It is also called as cutting ratio. So chip thickness ratio is represented by R, that can be calculated by T naught divided by what? You know that there are multiple formula there. T naught by TC is exactly equal to LC divided by L naught. LC divided by L naught is exactly equal to VF divided by VC. VF divided by VC can be calculated as sin phi divided by cos of phi minus alpha 0. Sin phi divided by what? Cos of phi minus alpha 0. These are the multiple ways by which chip thickness ratio can be calculated very easily. And now there is one more, that is called chip reduction coefficient, that is exactly R dash is equal to 1 by R. 1 by R, simply 1 by R, chip reduction coefficient. As we know that sir, TC value, that is thickness of the chip, is greater than T naught. So chip thickness ratio R is always less than 1, and chip reduction coefficient is always greater than 1. Always what? Greater than 1. I hope you are understanding this particular drama. Now specific energy in machining operation. What is specific energy? Amount of energy required to remove unit volume of material. So amount of energy required to remove unit volume of material, that is joule per millimeter cube. And in recently it has been observed that number of questions are asked on this. So therefore formula is specific cutting energy. Specific cutting energy exactly equal to, I'll say, power divided by material removal rate divided by material removal rate. Material removal rate. You'll say that's how. Let's say power, rate of consumption of energy, that is joule per second. Right, fine. Then I'll say that material removal rate. What is that? Mm cube per second. Mm cube per second. So second will get cancelled. Can I say unit is coming joule per mm cube? Joule per mm cube. So this is the specific cutting energy. Amount of energy required to remove unit volume of material. So I'll say specific cutting energy is exactly equal to power is what? Fc into Vc divided by material removal rate, can be simply written as feed into depth of cut into cutting velocity. Into what? Cutting velocity. Please take care of units. Please take care of unit. This is the most important equation nowadays to solve number of numericals. Now sometimes I can ask you simple one, specific energy of shearing. Specific energy of shearing or specific energy of the friction. So you can able to calculate that. So energy, that is total energy. Instead of total energy, we have to write down what is that? Specific energy of a shearing. Right, fine. That is exactly equal to shearing power divided by material removal rate. What is shearing power? Shearing, that is nothing but called as shear force multiplied by shear velocity, that is shear force Fs into shear velocity Vs divided by what? Feed into depth of cut into cutting velocity. Therefore as a specific cutting energy of friction, right? Specific cutting energy of friction, that is exactly equal to frictional force F multiplied by chip flow velocity divided by material removal rate. Again I'll say that feed into depth of cut into cutting velocity. Now total power, I know that total power is exactly equal to Fc into Vc, right? Sometimes I'll ask the question, calculate a shearing energy. So I'll say that shearing energy. So what will be a shearing energy? Can I say shearing energy is equal to shear force multiplied by shear velocity, and frictional energy is nothing but exactly equal to the friction force multiplied by a chip flow velocity Vf. So these are the multiple formulas are there by which you can be able to solve numericals, whatever it may be coming in a GATE examination. Whatever it may be coming in a GATE examination. So I hope so you must have enjoyed this. So like the session, subscribe it. All the best, my dear friends. Thank you.